Hello everyone, I am Himanshu Vasnani. I am from Department of Mechanical Engineering. Today I am here to present a lecture on material science. The subject is material science and the code is ME 207. Today we are studying unit number 2, lecture number 1. And today's topic is ductile and brittle fracture and ductile to brittle transition. So the our objective for today's lecture is to provide the students with a basic understanding of ductile and brittle fracture, ductile to brittle transition, and our outcome after studying today's lecture will be the student have learned the basics of ductile to brittle fracture and parameters of ductile to brittle transitions. So let me start off with today's lecture. So fracture, we have listened this term many times in our lab also and in our other subjects also. The fracture means separation, something divided into two or more pieces, something broken. So here we can say that fracture can be defined as the separation of a specimen into two or more parts by an applied stress. So fracture can be classified either as brittle or ductile fracture. Okay, we know that in our labs we normally undertake many tests, and in that test there are also tests in which a material breaks down. So depending upon the type of material and its crystal structure, it either it takes time to break, like it elongates and then it breakdowns, or it suddenly breakdowns. So these materials are classified under ductile and brittle fracture. You can say the former occurs with after little or no plastic deformation, whereas the latter occurs after extensive plastic deformation. So we have to understand that what is the basic difference between these two ductile and brittle fractures. So the differences lie in material fracture in ductile fracture. The material fractures after plastic deformation and slow progression of the crack, and in brittle fracture the material fractures with very little or no uh, plastic deformation, that is in a china clay, glass, etc. In ductile fracture what happens is the fractured surfaces are dull or fibrous in appearance. These fractures, they normally they are dull or fibrous in appearance, after breakdown of after happening of ductile fracture, the fracture surfaces are already crystalline in appearance. And if you go with the ductile fracture, uh, you can say the workpiece will be either fibrous or dull in nature. Next is in ductile fracture, the percentage elongation is about 30% prior to the prior to fracture occurs. Means there is a possibility that around 30% of elongation is about 0.5% or almost nil prior to the fracture occurs. So here you can see that what is the difference between the percentage elongation. So you can understand that what kind of difference they must be having when it comes to ductile and brittle fracture. 0.5% elongation, can you imagine? Just 0.5% or almost nil when you go for when the fracture occurs in brittle fracture, and in ductile fracture 30% elongation. Okay, it is a good value, person of percentage elongation when before the fracture occurs in ductile fracture. Then in ductile fracture, this is reduction in the cross-sectional area of the specimen. That is true if elongation is happening in a particular area, then you also understand that there is a reduction in the cross-sectional area of the specimen. And in brittle fracture, there is virtually no change in the cross-sectional area because the elongation is not happening, and that is almost nil whatever is happening. So as such, the cross-sectional area will not change in it. Okay. Then in the ductile fracture, the fracture takes place after necking with little sound. Whereas in brittle fracture, the fracture occurs rapidly, often accompanied by a loud noise. See, you might have seen in your day-to-day life whenever you broke a glass or heavy material, you say loud sound comes and then accompanied with a fracture and the scattering of the workpiece or the you can say material happens into breakdown. Now you can see that a sound is coming because in brittle fracture it is having suddenly no elongation. Whereas in ductile fracture, what they do, it elongates the cross sectional area is decreasing up from and after deformation and after a particular limit it will elastic limit will end and a small portion is available and at that point necking will happen and a little sound will come and it will break. So these were the common differences between ductile and brittle fracture, which you all must know and understand in order to make it, you can say, practice in your day-to-day life. Why? Because in the lab, when we are studying about materials, these kind of properties we should know that whether the material is has ductile fracture property or whether the material has brittle fracture property. So we should know, or based upon the data and the experimentation, we can say that this material has ductile fracture properties or this material has brittle fracture properties. So we should be aware of these two kinds of fracture. Now fracture is caused by the physical and the chemical forces and takes place in two stages. The first stage is either crack initiation, that is initial formation of a crack, and second is crack propagation, that is spreading of the crack. Now what happens during this time that in the crack initiation, whenever the crack is formed, you have seen in your day-to-day life that after a particular time that crack that is formed and if some forces are applied on it then the spreading of the crack takes place. Okay, so in this way the fracture is caused, the fracture takes place. Firstly, the crack happens, a small crack, an initiation is there, and after that, a crack spreading of the crack is there, which is called as crack propagation. If these two steps happen, if these two stages happen, then it will lead to fracture. So we should try, in order to avoid fracture, we should avoid these two stages also. If the initial stages avoided, then the second stage will automatically get avoided. Now metals exhibit different type of fractures, like which depend upon like type of material, then rate of stressing or loading, that is loading, then state of stress, and then temperature. Now depending upon the you can say the type of material, obviously a harder material and a softer material they will have different types of fracture types. Okay, why? Because you cannot press a hard material, whereas you can press a soft material. So there is a difference in the type of fracture. If you have a ductile material, sorry, you can say if you have a material which is porous in nature, it will have different type of fracture. So depending upon the type of material and the crystal structure and their properties differ according to the structure. So the different type of fractures will happen. Then rate of stressing, that is loading, then how much you are putting stress, though it is depend upon stress also. Then state of stress, okay, and then lastly the temperature. See, the temperature is very important because what happens that when if it is at room temperature, then the state of the workpiece is different. When you increase the temperature, the state of the internal atoms, that also differs, and then the fracture style or that is also will differ. So these four points should be considered, that depending on which the metals will exhibit different types of fractures. Okay. Now the main type of fractures shown by metals are brittle fracture, shear fracture, cleavage fracture and ductile fracture. These four kind of fractures I'll be showing you in the next diagram, which will be helpful to you. It will showing you that okay, these are the types of fractures observed in metals subject to uniaxial tension. Right, A is the brittle fracture, B is the shear fracture, C is ductile fracture, and D is completely ductile fracture. You can see in the C and D, you can easily see that ductile fracture is happening. The neck has been formed, and the D, if you can see that at the neck the fracture takes place with a little sound, and the complete ductile fracture happens. You can see the two different areas having different cross section. Whereas if you see in the A that is having a tile fracture, you can see there is no neck formed at that. Simply the fracture has happened. So in this way, these are just elementary diagrams showing you that okay how the fracture may look like. Okay, so it is giving you a slight idea. Not brittle fracture. The word brittle is associated with a minimum of plastic deformation, that is, with a little brittle fracture, the material fractures with very rapid propagation of a crack. Okay, I am to repeat once again. The word brittle is associated with a minimum plastic deformation with a brittle fracture, the material fractures with very rapid propagation of crack, with little or no plastic deformation like a china cup. I give you an example in that only. That first of all, what happens? A small crack takes place, and then the crack propagates, which lead to the deformation or plastic deformation. So this is what is called as brittle fracture. Okay. Now the salient features of brittle fracture are: the brittle fracture occurs when a small crack in a material grows, and the movement of crack involves very little plastic deformation of the metal adjacent to the crack. Now, growth continues until fracture occurs, that is, crack propagation. So, what happens that the brittle fracture it occurs when a small crack in the material grows. That is the first step in the crack propagation. That is the small crack in the material groove. It may be due to physical factor, it may be due to chemical factor. It depends, okay, upon the state of the material. And the movement of the crack involves very little plastic deformation. Now the crack is propagating, moving of the metal adjacent to the crack, right? Now crack growth continues until the fracture happens. Now the crack is propagating, and you know if there is no there is no deformation, or uh, you can say elongation, then the growth continue and the fracture will happen. So here the growth continues until fracture occurs. You can see all that crack propagation. So at the surface of a material, the atoms do not have as many neighbors as those in the interior of a solid, and therefore they form fewer bonds. They see at the surface of the metal, you know that the atoms do not have as many neighbors because they have below them their neighbors, not on the above. So as those in the interior of a solid, and therefore they form fewer bonds because they don't have on the upper side any you can say atoms they which from which they can make call them as neighbors. So in the interior they have that, so only the bonding is with the interior only. So surface atoms are at a higher energy than the plane of interior atoms obviously. So brittle fracture contains in destroying the interatomic bond by normal stresses. Okay, so brittle fracture contains in destroying and interatomic bonds by normal stresses. Now, this is a small example showing that how the brittle fracture takes without a little plastic deformation. But here, what happens in ductile fracture? See, it is taking time, and the elongation is happening, and the Necking will come, and after a particular time, after necking, the ductile fracture takes place. And you can see in the diagrams at the bottom that how after the fracture the workpiece looks like. It is having a you can say mild steel rod with it, and after breakage of ductile and brittle fracture, see how difference is there in their shape at the fracture zone. Okay, you can compare the ductile and brittle fracture very easily. So this diagram was for your idea, for your understood that might looking at the fracture zone only, might looking at the zone where the fracture has happened, you can easily tell that this fracture is either a brittle fracture or a ductile fracture. Okay, understood. I hope you have understood the point. Okay, now brittle fracture. Next, next points for this. Brittle fractures. What you are studying? Brittle fracture. Brittle fractures in materials in metals is characterized by a rapid rate of crack propagation with minimum energy of absorption, with no gross deformation and very little micro deformation. Okay, what happens that in brittle fracture, the very it is said that very rapid rate of crack propagation is happening with very little absorption of energy. Okay, so what happens that the adjacent parts of the metal in brittle fracture are separated by just normal stresses to the fracture surface. Okay, whereas if you say about ductile fracture, this does not produce plastic deformation and therefore require less energy than ductile failure, where energy is introduced in the process of forming dislocation and other imperfection within the system. Because suddenly the crack propagation is very fast, so they don't require any energy. So less energy is absorbed if you compare with the tactile failure. Tactile failure also require energy, but it requires more energy than the brittle fracture. Okay, because in ductile the elongation will happen, the elongation will take, so energy absorption is there. So, in brittle fracture occurs along crystal planes with fewer atomic bonds, that is characteristic stratigraphic planes called as cleavage planes. So, these the fracture is termed as cleavage fracture, very easy to understand. Now, brittle fracture occurs at or below the elastic limit of the material. Why? Because if it is very below elastic limit, then automatically you can understand. So, brittle fracture occurs at or below the elastic limit of the material. Then the brittle fracture, more information. Normally, brittle fracture allows the grain boundaries which can be identified by their granular and shiny look. Okay, so you can identify with the shiny look and then maybe brittle fracture might have happened. So in some instances, this type of fracture can cause a grain boundary film of hard brittle second phase. I told you earlier also, like that formed by bismuth and copper. The tendency for brittle fracture that increases with the increases with decreasing temperature. The tendency for brittle fracture increases with decreasing temperature, increasing strain rate and stress concentration conditions, usually produced by a notch. Okay, now brittle fracture is to be avoided at all cost because it is very dangerous and occurs without warning and usually produces disastrous consequences. You all know that whenever glass breaks, you all understand that it scatters and it is so risky that it has pointed ends which may be harmful to a person. So we should be should say avoid brittle fracture at all costs. You know that the tendency for a brittle fracture increases with decreasing temperature, increasing strain rate and stress concentration condition usually produced by a notch. So brittle fractures are of a practical importance due to failures of pressure vessels, bridges, pipelines, hulls of ships, etc. As you can see in this diagram, there is, you can say, a rod fixed, yeah, or you can say fixed in a vise. and a table and a hammer is used to apply some force. Now, if the material is brittle enough, then it will break down after a certain time. But if material is tough, it will show resistance to breaking. And so, in this way, also you can understand that this material, what is actually brittle. Okay. Then ductile fracture, the common name that is always along with the brittle failure, ductile fracture. So this signifies large plastic deformation and occurs after extensive deformation prior to and during the propagation of the plant. I repeat, this signifies large plastic deformation and occurs after extensive plastic deformation prior to and during the propagation of the cat. We understand that a certain amount of plastic deformation happens and after that the fracture occurs. So this plastic deformation, extensive plastic deformation, requires considerable energy which is absorbed in forming dislocation and other imperfection defects in the metal. So here this requires energy as compared to the brittle fracture. See, this is a simple diagram showing this brittle and ductile fracture. So you can see that these are tensile specimens, and in the brittle fracture, you can easily see that how the surface is look like. There is no kind of necking forming or not any elongation. Just a simple breakdown is shown. Whereas if you see the ductile fracture, you can see there is a necking going on. A kind of a cup and cone fracture has taken place. You can see the two specimen on the right hand side. Okay, the cup and cone fracture. It is easily shown that there is some kind of curve on the up and bottom portion. So ductile fracture has happened. So might by just looking at these diagrams, you can easily understand and tell that okay, so like test sample of specimen begins necking and minute cavities form in the neck region. The plastic deformation is concentrated in this region and indicates that the formation of cavities is closely linked to the plastic deformation. Hence, to the dislocation movement, thereby taking the longest time in the fractures. The region in which plastic deformation is happening, that is the dislocation. That is what this that is called dislocation movement. So it takes a long time for the fracture process to happen. I again repeat that the whenever this ductile fracture is happening, so the area where this dislocation movement is happening. So due to this dislocation movement, it takes long time for the fracture process to happen or to take place. Okay, we should be aware that this requires energy. This movement requires energy, which is absorbed during the ductile fracture process. Okay, so the cavities coalesce and form minute cracks or at the center of the test specimen, and the crack propagates outwardly to the surface of the specimen by shear separation in a direction 45 degree to the tensile axis, resulting in a familiar cup and cone fracture. So this I have shown in the diagram only that how the cup and cone fracture takes place. And this point has been explained by this lecture only that the crack propagates outward to the surface of the specimen by a shear separation in the direction of 45 degree to the tensile, resulting in a familiar cup and cone fracture. Now the various stages involved in ductile fracture are shown in figure. Here I'll show you this figure. Now what happens that the necking begins at the points of plastic instability where the increase in strength due to strain hardening fails to compensate for the decrease in the cross section. Necking begins at the points of plastic instability where the increase in strength due to strain hardening fails to compensate for a decrease in cross-section area. Now this occurs at maximum load. The formation of neck introduces a triaxial state of stress in the region. I repeat once again. Uh, the this occurrence in cross-sectional area, this happens at maximum load. So the formation of neck introduces a triaxial state of stress in the region. Okay, a hydrostatic component of tension acts along the axis of the specimen at the center of the neck region. Okay, hydrostatic component of, I'll show you all this in the diagram. Hydrostatic component of tension acts along the axis of the specimen at the center of the neck region. Many fine cavities in this region, like in the figure. Under continued straining, these grow and coalesce into a central crack. See this diagram. See this diagram showing you changes in the ductile fracture of a specimen. Tensile test. Okay, the specimen is there, it is loaded. Whenever you apply force, try to stretch it. So what happens that the neck formation takes place, showing you triaxial forces. You can see the arrows in the figure B in the center, which is showing in 3 dimensions. So in the figure C, you can see that some kind of neck has been formed and it has started formation of necks atom. And the figure D in the just before the fracture, there is, you can say, there is the end of neck formation. It will not, you can say, deform more than that net after the end of neck formation. It will simple break lead to fracture or breakdown, and this is what happens in figure E. So you can see that in the center of figure E, there is a kind of a cup and cone formation on the in the specimen. You can see there is a cup and cone formation showing that okay, ductile fracture has taken place. So this kind of normal procedure of elongation and then neck forming and then fracture is very common in ductile fracture. These are the common stages of a specimen in a ductile fracture. And let's go ahead. Now the crack grows in a direction perpendicular to the axis of the specimen until it approaches the surface of the specimen. So it then propagates to the surface of the specimen in a direction roughly 45 degree to a tensile axis to form the cone part of the fracture. One can also explain the fracture of ductile material in terms of work hardening coupled with crack nucleation and growth. Okay, so this is very important. This crack grows in a direction perpendicular to the axis of the specimen under it approaches the surface of the specimen. Now the initial cavities are often observed to form at foreign inclusions where gliding dislocations can pile up and produce sufficient stress so that the void or microcrack is formed. Okay. Now what happens that you can say that the test specimen is subjected to a slowly increasing load. So material begins to work harden where the initial elongation the permanent elongation and the cross sectional area at that point gets decreased. So in this way, the you can say the plastic deformation is happening inside the material, and then the associated decrease in areas that leads to formation of the neck because at some point the area will become less and it will get less and formation of neck and the formation of neck at the test specimen will be. Now, due to high dislocation density of the neck region and the material being subjected to complex stress, no longer a simple tensile stress, then the dislocations are separated from each other due to repulsive interatomic forces. Now, these dislocations they come closer with the increase of the resolved shear stress on the slip ring. The cracks are formed due to high shear stress and the presence of low grain boundaries. I repeat, the cracks are formed due to high shear stress and the presence of low grain boundaries. Okay, they are having a high shear stress and they are having a low grain boundary, so in that way the cracks are formed. So once a crack is formed, then it grows and elongates by means of dislocation and slip. The crack propagation for this mechanism is along the slip plane and these cracks coalesce. Obviously, one crack grows at the expense of other and finally crack growth results in slip. So in this way, ductile failure takes place, ductile fracture happens. Okay, so the common examples are that rock, concrete, glass, cast iron have a property of ductile materials. Property they can be called as ductile materials. Sorry, brittle materials. And so they may break down with very uh, nil plastic elongations. And ductile fracture means fracture of a material in the large plastic deformations. So before fractures, so like fracture of soft steel and rubber and plastics, these are all ductile fractures. Rock, concrete, glass, and cushion, these are all brittle fractures. So we should be aware of that. Then, if you want to have comparison when parameters are there and you want to compare ductile and brittle fractures, and you can say that the strain energy required is ductile is higher and brittle is lower. Then the stress during cracking is increasing ductile fracture, whereas brittle is constant. Then crack propagation it is slow in ductile fracture and brittle is faster. Then warning sign. In brittle fracture, it is plastic deformation, whereas in ductile fracture, it is plastic deformation, whereas brittle fracture, it is none. In deformation, you can say there is extensive deformation in ductile fracture, and there is little deformation in brittle fracture. Now, when it comes to necking, yes, there is a necking in ductile fracture, and in brittle, it is no neck. Then fractured surfaces, these are rough and dull when it comes to fracture surface of ductile fracture, and it's smooth and dry when it comes to the fractured surface of a brittle. Then type of materials, like most metals, they have ductile fractures, and in terms of brittle fracture, like ceramics, glass, ice. So these are all examples of brittle fracture. Now, ductile to brittle transition. This is also very important. That's why we have to discuss this also. This is commonly observed in BCC metals and almost missing in most of the FCC metals. BCC is body-centered cubic structured metals, and FCC is face-centered cubic structure. Okay, this transition is observed at low temperatures, extremely high rate of strain on notching the material. This is very important when selecting materials for engineering purpose. Now, what are the examples of ductile to brittle transition? Transition from ductile to brittle happens. It's called as transition transition. It is converting from ductile to brittle. So it is an important thing. So one can explain the ductile to brittle transition with the help of the figure that I'm showing you. Okay, it shows the plot fracture stress and yield stress as a function of temperature or strain rate. So here, sorry, here in this diagram you can easily see this is diagram number 42. Okay, ductile to brittle transition as a function of grain size and temperature. So you can see there is a line CD, okay, showing the region, and it has a transition region around that. Okay, in the upper side it is showing grain size, on the left hand side it is showing temperature. Okay, so and in the bottom. And the transition gain size dislocation. And then you can say that there is the transition region in which the whole transition takes place. Then there is okay, you can say that there is a stress for fracture or stress for using plastic. And you go for the transition temperature. So what happens that during this thing you can easily see that how the transitions take place. Now in the diagram, the curve for the brittle fracture stress rises slightly to the left because the energy surface, so the surface energy increases as temperature. So we saw that the strong temperature dependence in the yield stress curve in a BCC metal and metal oxide cell. From the figure, it is clear that two curves intersect and a vertical line is drawn at the point of separation. Okay, which is called as ductile to brittle transition temperature. I repeat, it is only that two curves intersect and the vertical line is drawn at the point of intersection, which is called as ductile to brittle transition temperature. Now, if a material is stressed and at a temperature or strain rate which is to the right side of line CD, it will reach its yield point prior it reaches the brittle fracture stress. Okay, will undergo some plastic deformation prior to fracture. So here, uh, plastic deformation will happen. Okay, before fracture. Now, however, applying a stress again under condition which lie left on the line CD. CD is the common line. Okay, which results in ductile fracture of U. Okay, so obviously at all temperatures below the transition temperature, the fracture stress is smaller than that of the yield stress, and this reveals that fracture stress may be controlled by the yield stress as the applied stress reaches a value equal to the yield stress. So the crack is nucleated at the intersection of the slip planes and propagates rapidly. So the temperature range over which the rapid changes takes place, it is termed as the transition region. Okay, the temperature range is called as transition region. You have seen this transition region I have told you. See the gray part, transition region. In the center, on the left hand right hand side of CD line, there is a transition region. This is the temperature range. Okay, you can see at the bottom there's a temperature showing arrow. So this is the temperature range. Okay, and there is a transition temperature also shown at the point D also. So you can understand the importance of this in this topic. For mild steel, the consumption of energy in an impact test as a function of temperature is shown below this. Okay. Then by fast loading, one can achieve a strain rate in impact testing machines. We know that increasing the strain rate is equivalent to lowering the temperature. So we have to be careful. This means that the materials that are ductile when strained slowly at a given temperature will behave in a brittle behavior when set to a high strain rate. Okay. So the ductile to brittle transition is quite dangerous from design point of view. Okay, this is mild steel. For mild steel, the variation of impact energy, the function of temperature. At the bottom there is temperature. You can see how it is transiting. Okay, you can see that. So this is a simple graph showing the transition temperature and the variation of impact energy in function of temperature for mild steel. So now fatigue failure. Now fatigue, it is a failure of a material by fracture when subjected to a cyclic stress. Okay, cyclic stress means you are something applying for stress on. So it is a failure of a material by fracture when subjected to a cyclic stress. In which you take a workpiece and apply stress, cyclic stress. So fatigue can occur at a stress whose amplitude is much smaller than the static load required to produce the fatigue. The maximum stress that a material can withstand without failure for a specific large number of cycles of stress is termed as fatigue or endurance limit. Okay, I repeat, The maximum stress that a material can withstand without failure for a specific number of stress cycles of stress is termed as its limit, fatigue limit or endurance limit. This is very important. How much cyclic stress it can hold. Okay, it's called a fatigue limit or endurance limit. So fatigue is distinguished by three main features. Okay, this fatigue you can say the fatigue limit or endurance limit, or this fatigue is distinguished by three main features. One is the loss of strength, loss of ductility, and increased uncertainty in the strength and service life. Now, engineering materials are often subjected to fluctuating loads while in service. Obviously, in service, it will lead to some kind of fluctuating loads, common thing. So, few examples of components which are subject to fluctuating loads are aircraft wings related to turbulent air, then leaf spring and to and fro, then you can say connecting rod pushed and pulled in piston engine, and some parts of compressors, pumps, turbines due to repeating loading and vibration. So this is the working, and during service, working is these are the components which okay deal with fluctuating loads and alternate stresses. So they have tell them. So if a metal wire is bent to and fro several times, okay, you are bending a metal wire to and fro several times. It appears ultimately breaks down at a point. Rotating and vibrating parts of an engine in aeroplanes are liable to undergo fatigue and other accidents. Huh? And fatigue fractures occur without any warning. They result in brittle fracture. About 80% of the failure in engine components takes place due to fatigue failure. Okay, you understand? You are it also occurs without any warning. So around uh, they result in brittle fracture. Okay, the steels have generally a fatigue limit which is normally zero point 0.4 to zero point 0.5 times the tensile strength of the material. The steel they have generally a fatigue limit which is normally zero point 0.5 to zero point 0.4 to zero point 0.5 times the tensile strength of the material. Zero point 0.4 to zero point 0.5 times, can you imagine? Okay, it's really. Under following conditions, the fatigue fracture progressively rapidly happens, like the maximum tensile stress at sufficiently high values and large vibrations of fluctuations in the applied stress, then large number of cycles of applied stress and other variables which may change the condition of failure, such as stress, concentration and overloading, corrosion, residual stress, etc. So these fatigue fracture it happens. Uh, so I think that should start off with these properties are there like corrosion, surface finish. We all will discuss it later on, like temperature, microstructure. I think of an alloy, the residual stress and heat treatment, stress concentration. So we will discuss it. Now we start with the MCQ. Then fracture is defined as a separation of a specimen into two or more parts by an applied stress, which can be classified as either brittle or ductile. So it is true or false. It is true. True. Okay. Then the second question comes: the brittle fracture occurs after little or no plastic deformation. So is it true or false? It's true. You should know. The ductile fracture occurs after extensive plastic deformation. You can compare it to ductile and brittle fracture. This ductile fracture occurs after extensive plastic deformation. So this is somewhere true. This is true. So metals exhibit different type of fractures. You can have you understand this question no? This ductile fracture occurs after extensive plastic deformation. It is true. Now, metals exhibit different types of fractures, which depends upon like the type of material or rate of stressing and loading, the state of stress or temperature. So, all these kinds of the properties of the material we should consider for that. Then the word brittle is associated with the minimum plastic deformation, that is with a brittle fracture, the material fractures with very rapid propagation or crack with very little or no plastic deformation like a china. Is it true or false? Okay, it has given you a simple, you can say, definition of a brittle fracture. So you can understand that what kind of saying with little or no plastic deformation is true. Okay, then again, the temperature range over which the rapid changes takes place is termed as a transition region. We are just studying about that transition region. Okay. Then fatigue is distinguished by which features like loss of strength, loss of ductility, or increased uncertainty in strength and service life. What do you think? The answer is D. All. All these features are required. And stronger ductile material metals. But the odd statement about ceramics is going that ceramics are ductile in nature. This is a odd statement. Ductiles are not. Okay. You find out the odd statement about ceramics in the following. So the odd statement is that ductile in nature. The answer is C. Fatigue fractures occur without any warning. Any guesses? It is true. It is true. So in today's lecture, I have tried to cover uh, all those topics. All those important, you can say, discussions required for the tile and brittle fracture. And also I've given you some visual you can say images which will be helpful to you in understanding the topic deeper. But while working in the workshop you should always be aware. Okay, while working either in workshop or any industry you should be aware that okay, if such kinds of symptoms are shown after fracture, so you can identify that it can be a ductile or it can be a brittle fracture. Okay, so these are the references which you should refer, and these references contain contents, and if you want to have more knowledge about this today's lecture, then you can go with these books, read them, understand them. It will have more content, it will have more diagrams, which will give you more knowledge. But understand one thing, that when you study, try to understand things which will make you, you can say, absorb knowledge. Okay, so today, for now, today's, uh, so thank you all. Thank you all.